Hello ladies and gents, Daniel here from Rock the JVM. This video is a highly popular and requested topic for the YouTube channel, so I figured I would talk about linear collections in Scala. Now, this also happens to be a dedicated lesson in the recent Scala and Functional Programming Essentials course I've just re-recorded and updated for Scala 3, and you can find a link in the description below. So here you'll have an extract from the course where I show you exactly how linear collections work and how to use them. So with that introduction out of the way, let the lesson begin, and please enjoy. Alright boys and girls, welcome back. So now that we've established some foundations in working with object orientation and functional programming in this chapter, we're well equipped to start working with some standard Scala library data structures, starting with linear collections. So this is what we're going to discuss in this video. Now, most of the ideas that we're going to lay out in the code, you're also going to find in the slides of this lesson that you can find either here attached to this video or to the beginning of the course, where I will attach all the slides of the course, and they will serve as kind of like a recap or a cheat sheet for you. So I'm going to create a Scala application for this video. I'm going to name this linear collections, and I'm going to make it an object as usual, and I'm going to create a main method because we're going to test a bunch of stuff. So in this video, we're going to discuss linear collections in Scala. There are quite a few, and each serves a different purpose. I'm going to start with a data type, a very general interface, or a very general trait, known as a sequence, known as SEQ for short. Now, SEQ is a trait that describes a linear collection of objects that are ordered. So we have a well-defined ordering and indexing. That is, we can access an element at a particular index of the sequence. And in order to create a sequence, you can create a sequence, and I can use the apply method of the companion object of the seek trait. So I can apply seek to a bunch of arguments, for example, 1, 2, 3, 4. Now this will be an implementation of sequence. Now you don't necessarily know which implementation of sequence this apply factory method will return. All you know is that this will be a sequence of integers. Now the main API of a sequence is to be able to index a particular element. So let me define a simple method called test SEQ. And I'm going to test a bunch of stuff here for every single collection. And I want to separate my use cases here. So the main API is to index an element. So for example, if I'm interested in the third element of this sequence, the number 3, I can say third element as a sequence. And I can say a sequence.apply. And the argument to apply is going to be an int, meaning the index at which I want to access the element. And I'm going to use the index 2 because sequences are 0 indexed. So this will be the element 3. Now, sequences are much richer than that, and they have a bunch of other methods. For example, the ability to reverse a sequence, let's call this reversed, as a sequence.reverse. And this will be the sequence backwards, and that is because we have the well-defined ordering here. We also have the ability to concatenate, so I can say concatenation as a sequence ++, and I can add another sequence here. For example, I can use 5, 6, and 7. And this will be a sequence containing all the numbers 1, 2, 3, 4, 5, 6, 7 in sequence, in order that is. And a sequence also has the capacity to be sorted. That is because it can keep on ordering, and so it can keep on ordering of my choosing if I want to sort the sequence in a particular way. So I can say, let's call this sorted sequence as a sequence.sorted. Now, sorted is a little bit more magical method because it automatically fetches an implicit ordering for the type that the sequence is typed with, in this case, an ordering of integers, and the compiler automatically has access to that because integers are naturally comparable. And this will create a sequence with, in this case, 1, 2, 3, 4, because it's already sorted. But if I had said something like 4, 2, 3, 1, then this sorted method will return the sequence 1, 2, 3, 4. And if you're curious, you can print a bunch of stuff. So print line, a sequence, Then I'm going to print line concatenation just to prove that we have all those elements in order. And I'm also going to print line sorted sequence if you'd like. And in main, I'm simply going to call this method test seq, and we should obtain the sequence 4231. Then we have the sequence 4231567, and then the sequence 1234. Notice that all of these sequences are lists. That's because the factory method here, the seq.apply method, which is being called at this line number 7, will return a particular implementation of sequence that's not necessarily under your control. And in this particular case, it returned a list because a list being an ordered data structure, it conforms to the trait sequence. And so list extends the seq trait. Now, besides these pretty useful APIs, the seq trait also has the map flatmap filter and also supports 4 comprehensions in the style that we discovered in the previous videos. So we have map, flatmap, and filter, and also with filter. So I'm going to add a 4 comprehension here, and I'm going to give a bunch of examples. Let's say a incremented or unincremented sequence as a sequence map underscore +1, and this will be the sequence 5, 3, 4, 2. Then we have flat mapped. Let's call this a flat mapped sequence as a sequence flat map, and for every element I'm going to return a seq with that element and that element +1, and in this case we will obtain the sequence 4, 5, 2, 3, 3, 4, and then 1, 2. And also filtering, so I'm going to say a filtered sequence as a sequence filter, and I'm going to use underscore mod2 equals 0. That's the simplest kind of filter. In this case, we will obtain the sequence with the even numbers, in this case 4, 2. All right, so because we have map, flat map, filter, and also we have with filter, we're eligible for 4 comprehensions. So you can use sequences and 4 comprehensions, no problem. So that was the first kind of linear collections, sequences. A particular implementation of sequences are lists, which you have seen before. So if I define a method called test lists, then I can add a bunch of lists here. You're already quite familiar with them because you also implemented one yourself. And I'm going to create a list as list with 1, 2, 3. Then you have the same kind of APIs that a sequence has, including map, flat map, filter, apply, so you can index a list. So I'm going to mention here, so same API as seq. So I'm not going to repeat every single thing that I wrote here in the sequence section, but for a list you have the capability of extracting the head and the tail. So you can have, let's call this first element as a list head. You also have the rest of this list, so rest as a list tail in the style that you wrote in the linked list implementation. Now, we also have the capacity to add elements at the beginning or end of this list, so appending and prepending. So if I want to add the element 0 at the beginning of the list and the element 4 at the end, I can write something like a bigger list as, and I'm going to write the following. I can say number 0 is added to a list, and then the list adds the number 4 at the end. Notice these kinds of operators. So we have the plus colon operator, and also this other operator, which is symmetrical. So we have colon plus. Now they're quite easy to confuse, and the rule of thumb that I use in order to not confuse these two operators is that the plus stays on the side of the element being added, and it's added at the beginning in this case, and is added to the end in this other case. Now, specifically for lists, we have a special flavor of prepending. Let's call this prepending, as I'm going to use 0 colon colon a list, which is by far the most used case of adding an element to the beginning of a list. Now, this operator, colon colon, is actually the apply method of the case class that we called cons in our linked list implementation, but in the Scala standard library, this operator here is actually the apply method of the case class that's called : exactly as it is. So : is equivalent to cons in our linked list. So if we go here and try to add an element to a list, we move to the method definition, notice that it creates a new instance of : So the : thing is a case class, which is an implementation of a non-empty list, much like we had on cons. All right, so this is the implementation in the standard library. Let's go back. Now, a very useful method in sequences actually, so I'm going to write it above in the other methods section, is to be able to combine all the numbers into one value. So I can write, for example, an expression that calculates the sum of all these values, and I can say val sum as a sequence, and I can use fold left in much the same style as we did on our own linked list. So I'm going to fold left with 0 and underscore plus underscore, and this will create the sum of the entire list. So 1, 2, 3, 4, that's the sum 10. And fold left belongs to the seek trait, and the linked list implements that fold left method in a particular way, quite similarly to what we did in our linked list implementation. We also have a useful method to combine all of these numbers under a string and create a string representation of this sequence. So for example, if I want to print the sequence as this kind of list, I can say, let's call this string representation as a sequence dot make string, and notice that we have a bunch of overloads here. So make string with a separator that's in between every single element, or make string with a start token, a separator in between two elements, and end. And I can use, for example, this, which is the beginning token, the comma in between two elements, and the closed square bracket to the end of that string representation. And make string is quite powerful if you want to serialize a sequence to a string. And the list obviously has that same functionality too. Now, coming back to list, we have some utility methods on lists as well. For example, you have the capability to create a list of a particular dimension with a default value inside. So for example, if I want to create Scala 5 times in a list, so I'm going to say Scala x5 or something like that, and I can say list.fill, and notice that fill has a bunch of overloads, and you can have fill with n in, so that's the number of elements, and the element being inserted there. So I can say fill 5 with the string Scala, and this will create a list of 5 elements, each containing the string Scala. Alright, so that was lists as a very used implementation of a sequence. I'm also going to show you another sequence implementation called a range. And ranges are a peculiar data structure in Scala in that they don't necessarily have to evaluate or actually contain all the elements inside. And I'm going to give you some examples. So I'm going to define a method called test ranges. And here I'm going to create a range object, which is a sequence of integers, for example. And in order to create a range, you will need to run a special method, which is called 1 to 10. So this 2 is a method on the int type. There's a bit of magic going here so that the 2 method can be applied to the int type, but more on that in the advanced course. But this kind of expression creates a data structure called a range. So if I remove the type signature, first of all, the type signature compiles, so this is a proper type seek int, but if I leave the compiler to infer that for me, it's a range.inclusive. This is a particular implementation of range, and this does not necessarily contain all the numbers 1 to 10. I can contain the range 1 to 10 billion, and the range will not evaluate them all, even though evaluating them all would crash my JVM. And ranges are quite smart in how we can evaluate certain things on them. So for example, I can have the entire API of a sequence, and I can have, for example, the capability of doing a fold left, but I don't necessarily have to hold all 10 billion elements in memory. All right, so we have the same sequence API. And ranges are very interesting and very useful when you want to do something a bunch of times, a specific amount of times. For example, if I want to print the string Scala to the console, I can say 1 to 10 and then dot for each. And here I can pass a lambda that takes an element of type int, and then I can say print line Scala. Now, if you're not necessarily using the argument of the lambda, you can place an underscore here to hide the name if you aren't using it. And this would print Scala 10 times to the console. So if I run this test ranges method in main, then I'm going to print the string Scala 10 times without actually holding all the 10 numbers into memory. All right, so we have this effect. And ranges can be of two types. This range is inclusive, so the elements 1 and 10 are quote unquote included. But if you have a non-inclusive range, you can also say 1 until 10, and the number 10, the upper range, is not included. So 10 not included. All right, so that was ranges. Let's also test arrays. So arrays are a common data structure on the JVM, and if you've worked with Java before, that should be like int square brackets. So these are the type of natural arrays on the JVM, and you might see similar definitions or similar types in other programming languages as well. And arrays in Scala are denoted by the type array. So let me define another method called test arrays. And here I'm going to create an array. And an array can also be built with a companion object, much like we had on lists. So we can say array with the elements 1, 2, 3, 4, 5, 6. And this will create an actual int array on top of the JVM. So the int array is not really boxed or modified in any way. This is an identical int square brackets on the JVM. Now, even though the array type doesn't officially belong to the type hierarchy denoted by seek or other linear collections, array also has access to most seek APIs. But arrays are not sequences, so I'm going to mention that here. So arrays are not sequences, but I'm going to show you how you can convert an array to a sequence. Is an array, and you can use toIndexedSeq method to convert that into an actual seek of int. Right? So this will be a seek of int. And an array, the main API or the main capability of an array is that it's mutable. Every single collection that we've discussed so far are immutable, and hopefully you've gotten quite accustomed to this principle of immutability. That is, when you want to modify a collection, you actually obtain a new one. Whenever you write map, flatmap filter, and so on, you obtain new collections. But with arrays, these are the first instances of collections that are modifiable in place. Now, if you want to modify an array in place, I can say an array, and then I can say update, and I need to pass two arguments of type int in this case. The first is the index at which I want to change the value. For example, I want to change the index 2, so I want to change the number 3 here, and I can change that with the number 30. So that means that the number 3 is updated to the number 30 without returning a new array. So no new array is allocated. So this is the main capability of an array, that you can modify it in place. All right, let's talk about vectors. Vectors are also linear collections, and they're very fast sequence implementations, and they conform to the seek API, but they're much faster when you have a lot of elements inside. So vectors are fast sequences for a large amount of data. So I'm going to define a small test, so test vector, or test vectors. I'm going to show you how you can build vectors. I'm pretty sure you got the picture or the pattern here. You have a vector, and we can build a vector through the companion object. So I'm going to say vector with 1, 2, 3, 4, 5, 6, whatever. So this will be a vector of int. And this one has the exact same seek API. It has no specific or pretty useful APIs on its own, but it's quite fast. And if you'll allow me a few minutes, I'm going to show you a small benchmark, a noobs-like benchmark, very, very simple, to show you how fast a vector can be compared to, say, a list. So I'm going to define a small method. I'm going to call this small benchmark. And here's what I'm going to do. I'm going to create a vector of 1 million elements. I'm also going to create a list of 1 million elements. And I'm going to show you what the average write time for a vector or for a list is. That is, I'm going to try to modify an element at a particular index, at random indices actually. And of course, when you modify a data structure, you'll obtain a new data structure. So I'm going to show you what the average write time or the average modification time for a vector is compared to a list. So I'm going to define some values here. I'm going to define a value called max runs. I'm going to test this for 1,000 times. I'm going to define a max capacity as 1 million elements. So I'm going to try 1,000 random accesses inside a 1 million element vector and 1 million element list. And for that, I'm going to define a small utility method. I'm going to define, let's call this get write time. And I'm going to pass a collection, which will be a seek of int, just to be able to conform to both vector and list. Both are sequences. And this will return a double. And I'm going to write the following. I'm going to instantiate a random number generator. You haven't encountered the random data structure, but it's quite easy. So I'm going to create a random as new random. And I'm going to import random from Scala util. And for 1,000 times, as max run says, I'm going to try to modify this collection and obviously return a new one. And because I need max runs, I'm actually going to put it at the top. So here's what I'm going to do. I'm going to say val times as, and I'm going to write a for comprehension, and I'm going to say I in 1 to max runs. So this will be a range, and I'm running a for comprehension on that range because it's also a sequence. And I'm going to yield an expression. And this code block will be the expression that I will obtain. And this expression will be the time computation of what it takes to create a new collection after I try to update an element at a particular index. So I'm going to create val index as random next int max capacity. So this will create a random integer from 0 to max capacity non-inclusive. All right. And then I'm going to try to update this collection at this randomly generated index. And so I will need to create, let's call this current time as system.nanotime. Then I'm going to do my thing. So I'm going to create an updated collection as collection dot, and there is an updated method. So updated takes two elements, an index and the element that I want to place there, and I will obtain a new collection. So I'm going to say updated at the index that I've just created, and the element I'm going to create one randomly. So I'm actually going to create a random next int. Let's create a element. And I'm going to try to place at this particular index the element that I've just computed. And then I'm going to return, as a result of this entire block, I'm going to return system.nanotime minus the current time that I created before running this updated thing. Now, this whole for expression is going to be a collection containing max runs elements because this is the thing that I'm mapping against. So I'm going to obtain 1,000 elements, and each of those elements is the time it takes for me to update this particular collection at a random index with a random element. All right. So now I will need to create an average for all these times. So I'll need to create a sum and then divide that by max runs. So I'm going to have times fold left with starting at 0 and underscore plus underscore, and you know by now how you can compute the sum of all the elements in a sequence. And then I'm going to multiply that by 1.0, and then I'm going to divide that by the max runs number of elements. Now the code shows red here because the number 0 is an integer, but times is an index sequence of long, so I will need to place an L here for my code to compile. So 0L is a long, not an integer. Now this whole expression here with fold left 0L underscore plus underscore can be further compacted to calling sum. So for things that can be summable, for which you have the addition operator, there is the sum method on a sequence. So you can sum them up on a single method call. So times.sum times 1.0 to convert this into a double, and then divide that by max runs to obtain the average of all the times. So I'm going to say compute average. So I hope this getWriteTime auxiliary method makes sense. Now, with this write_time method in place, we can now instantiate 1 million elements in a list and then 1 million elements in a vector. And the way that we can do that really quickly is convert that range to a list and convert that range to a vector respectively. So I'm going to say, let's call this numbers list and I'm going to use 1 to max capacity, and then I'm going to call toList, which is a very useful method in between all of these linear collections. You can have toList, toArray, toSequence, to whatever. So you can have conversion methods from and to every linear collection in the standard library. This is very powerful. And I'm also going to create a numbers vector as I'm going to use 1 to max capacity, and then I'm going to call toVector there. Cool. Now, I'm going to print the getWriteTime applied to numbers list and getWriteTime applied to numbers vector to see what we get. So I'm going to print line getWriteTime for numbers list and getWriteTime for numbers vector. All right. So in main, let's try this out. So I'm going to call simple or small benchmark, or however I call that, so small benchmark, and let's see what we get. So this is going to take a few seconds, but the results will speak for themselves. So notice that we have 5 million in the case of the list and 2000 in the case of a vector, and this is nanoseconds. So 5 million nanoseconds, that's 5 milliseconds on average to update a list at a random index. So here, in the case of vector, we have 2000 nanoseconds, so that's 2 microseconds. So that's more than 3 orders of magnitude performance difference between lists and vectors for a large amount of data. For small data, there is no substantial difference between a list and a vector. And if we change max capacity from 1 million to, say, 100, and if we try this experiment again, the numbers won't be that different. So notice that we have just maybe 1 order of magnitude, and if we lower the capacity, the complexity is probably going to be smaller still. So that's the difference between a vector and a list. I'm going to leave it back to 1 million in case you're curious and you want to test this yourself. Now, the final linear collection that I want to talk about in this video is a set. Now, a set is a particular data structure that does not allow duplicates. So I'm going to define a method called testSets, and I'm going to create a set. And as you may have noticed, we have a commonality in terms of construction. So we have set with the companion object supply method, for example, 1, 2, 3, 4, 5, and this will create a set implementation containing these 5 elements, of course, with no duplicates. So if I add the element 4 again, then the number 4 will not be added twice to this particular set. Now, sets are usually implemented in terms of equals plus hash code. That's because a popular implementation of the set data structure is the hash set. Now, set is a type in Scala with its own trait, so you can have it here. So trait set extends whatever, so you have a bunch of methods here, but the implementation of set is somewhere buried in the Scala standard library. Let's get back here. All you need to know is that a set doesn't contain duplicates. And the main API is to test whether an element is in the set. So for example, if this set contains the number 3, I should be able to test that by calling the contains method. So I'm going to say contains 3 as a set dot contains, and I can pass the number 3 inside and it should return true. So this returns a boolean. Also, the contains method is further compacted by naming that to the apply method of the set trait. So I can say val contains 3 as a different version, and I'm going to say a set apply to the element 3, and this has the exact same meaning. And because we have the apply method, obviously we can compact that and invoke set on the number 3, and this will return true. All right, now beyond the capability of testing whether a number is in the set, we also have the capability of adding or removing elements to and from the sets. For example, if I can say a bigger set as a set plus element 4, so this is me adding the element 4 to the set, and obviously this will contain a new set, and because the number 4 is already included, then we're going to obtain the numbers 1, 2, 3, 4, 5 here in this set as well. Not necessarily in the same order, mind you. The set trait doesn't really guarantee a particular ordering, so no ordering guaranteed. There are specific implementations of set, for example a tree set, that also guarantees an ordering if you care about that as well. Now, if you're adding an element to the set, you'll obtain another set regardless of whether that element is contained within the set or not. And obviously you also have the capability to remove the set, so let's call this a smaller set, as a set minus 4. And that'll be the elements 1, 2, 3, and 5, not necessarily in this same order here in the set. Obviously, we also have the capability of adding more than one element to a set by concatenation. So for example, if I define a val, let's call this another set for the lack of a better name, I'm going to create a set, let's call this 4, 5, 6, 7, 8. And then you can add all of these numbers to the set, much bigger set, as a set plus plus another set. So the same kind of operator that we saw on lists as well. This adds all the contents of the other set to this set, and obviously we'll obtain another set as a result. An alternative version would be to say a set union another set. Let's call this val much bigger set, not much bugger, much bigger set. And I'm going to name this v2 because it's much more compact. And this will be a set union another set. So unioning means that you are adding all the elements of the other set into a much bigger set. Also, we have a union alias known as the bar or the AND operator on Booleans. So you can have much bigger set v3 as a set bar another set. And this is an alias for union. So this will be the same as well as this one. So concatenation is also known as unioning. We also have some mathematical operators for difference. So for example, if I want to remove all the contents of the other set from me, let's call this a diff set as a set diff another set. So we have the diff method, or we have an operator there. We have a set, instead of plus plus, we now have minus minus. So we're removing all the elements of this other set from my set, and obviously we're going to return another set as a result. We also have the mathematical concept of an intersection. So that is all the common elements of two sets. And I'm going to have a set intersect with another set. And this will contain just the elements 4 and 5. And there are aliases there that look like mathematical operators. I'm actually going to have that as another line here, an intersection v2. And you can have a set, and you can use the ampersand operator, much like the bitwise AND operator on integers. And that's the main API of the set data structure, which is also a linear collection. Feel free to pause the video and try to test these operators if you want. Alright, so this was a comprehensive overview of linear collections in the Scala standard library. I hope you enjoyed it, and you will find these collections useful in your Scala programming life. I'm waiting for you in the next lesson.